got it now. Yeah, we have 3 examples here. Okay, we're gonna be doing 3 examples. We're just doing the first example. So, what's the moral of the story? You're given 2 points, and you want to find the exponential function that goes through these 2 points. So basically, what that means is that with the 2 points that you're given, you have this information. You have the value of the function at 2 different points. You set up the general form, which is b times a to the x, and your job is to find a and b. And what you know is that a has to be positive and different than 1. That's the base. So with the first point information, you're gonna get 1 equation. You plug in and you get 1 equation relating a and b. With the second point information, you plug in and you get another equation relating a and b. And then all you have to do is solve the system. Okay. And here the easier way is just to solve by substitution. Solve for 1 variable in 1 equation, plug it into the other equation, and then solve. Depending on the type of expression that you get, then that's what may make it a little bit more complicated, the algebra or not. Like in this case, we needed to deal with a lot of radicals because of the numbers that we have. Okay, but I mean, it's what it is. And so once you figure out your a, remember a has to be positive. That's how we were able to remove that negative option that we obtained. We just kept on simplifying a little bit until we found something nice, 6 to the negative 1 over 4. And once you have 1 value, then you use one of the equations to figure out the other unknown, which was b, which happens to be square root of 6 in this case. And then you write down your function. That's what's going on. Right. Questions on the calculations that we did here. We're not going to do example 2. Questions on any of the calculations that happen in this example. Right? Let's see. Let's take a look at number 2. Now, number 2 is something very similar to number 1. It's just that it's put into some context now. Okay, number 1 is very arbitrary. I give you 2 points and then find the function that passes through these points. There is no story behind these points. Now we have a story. So let's see. Let's read the story. Remember, every time that you want to do a word problem, you first need to read it and make sure that you understand what you're looking at. So a wolf population is growing exponentially. So they're already telling you that population grows exponentially. In 2011, 129 wolves were counted. By 2013, the population had reached 236 wolves. Write the equation representing the population n of wolves over time t. Right. So again, we're given a population of wolves, and we're being told that this grows exponentially. And they tell you that in 2011, the amount of wolves that were counted, and then in 2013, they tell you again the amount of wolves that were counted at that point. Using this information, we should be able to write down a formula for the population of wolves over time t. Do you understand this? Do you understand what the problem is saying? Right, so let's go for it. So first, let us now do a setup, okay? Now this is very important. Here we need to make a compromise. What do we want? When is it that we want to start measuring the time t? Okay, so note, do you want to begin t at the beginning of time, whatever that means? What was the beginning of time? Or do you want t to be the year 0? Or do we want t to begin at the year 2011? In other words, how is it that we're measuring time? Very good, Sarah. So the smart thing to do here is, because remember, we want to work with small numbers. Otherwise, when we have too big numbers, when t is too big, then 2001, 2013, you have to be dealing with these large numbers. So what's the standard to do is, according to the problem, they started measuring 2011, so that means they really care about what happened in 2011. Okay, they started moving forward. Okay, because they say over time. So our t represents the time after 2011. We're going to use our t to represent the years after 2011. So with this notion, for example, 2013, we correspond to a value of t equals 2. Does everybody understand this? equals 0 will be 2011, and then we start counting starting at that point. Otherwise, if you let t equals 0 be the 0th year, whatever that means, the point that we change from before Christ to after Christ, I guess, and we have to be dealing with all of these big numbers, 2011, 2013, and so on. Okay? The question really is interested in what's happening starting at 2011. So let's do it that way. We're going to count time starting at 2011. Everybody okay with this? You understand what I'm saying? All right, so we need to write that down because this is not written in the problem. So whenever, since we are the one creating the function, we are the ones that have to say what is our convention, okay? So we need to use n for the formula, but let's write down what n represents. So for number 2, then we're gonna say what that represents. So n of t, what does this represent? This represents the population, the population of wolves, after, or the population of wolves 3 years after 2011. Of course, it depends on t. You tell me what the value of t is, and then the output of our function is going to tell us how many wolves would there be, after this amount of years. Of course, this model that we're gonna produce is not really realistic because this is, you let it go, it's gonna grow to infinity. As you know, there are some restrictions on the wolf, right? Like, the more wolves there are, then the less food there will be, so they start to die faster, so population goes down. And the famous relationship between wolf and rabbits. When there are few wolves, there are a lot of rabbits. Then there's a lot of food, so the population of wolf grows. The more wolves are eating rabbits, so the rabbits go down, wolves start to die, so population of wolf goes down, rabbits goes up, and so on and so forth. That's a cycle that we go through, right? And then there are also constraints like space, like you can only have a finite amount of wolves living in a certain place. You can have infinitely many. So anyways, so this is not really realistic, but unless in a short period of time, let's say between 10, 20 years, is probably close to what could happen in the population. There are more realistic models that are called logistic models that take into account all of these things that I mentioned. Anyways, we're just using an exponential model here. All right, so population of wolves 2 years after 2011, that's what our function n represents. So with this in mind, with this setup in mind, let us go back to the problem and try to see what data we are given, okay? All right, so we now read the first sentence. Population of wolf is growing exponentially. So what information is encoded in this first sentence? This is telling you how n looks like, right? So sentence number 1 is telling me that this function that we are after, n of t, it will look like this, right? It will have this form because it's telling me that it grows exponentially. Everybody understand this? How we get this from the first sentence of the problem? Right, so let's come back to the problem and keep reading. Okay, next sentence, second sentence. In 2011, 129 wolves were counted. Okay, so what does this mean for our problem? In the language that we have been setting up about n of t, what does this mean about our function? What information are they telling us here in regards to our function? Anybody? So again, the growing exponentially part told us that n of t had this form, right? For some a and b. Okay, so for some, this first part tells us that n has a form b times a to the t. And of course, here our job is to find, this is for some a and b with a positive and different than 1. This is what we know from the first sentence. Now, I'm asking you, what's the second sentence telling us? information that in 2011 there were 129 wolves. But what is this telling us? How do we write this with our setup? So how do you write this mathematically? How do we use this sentence to our advantage? Anybody? See, let's be a little bit more specific. What is this telling you about the function n, which represents the population of wolves? Okay, I don't understand what you wrote, Maria. What do you mean by n plus 129 in parentheses t? So what is this sentence telling you about n? Let's see, who can tell me what does n represents? We wrote it down. So what does n of t represents? What's the meaning of n of t? Yeah, but that's not what I wrote. I wrote more. Everything I wrote is very important. It's not just number of words. I know it's number of words because that's given in the problem. But I wrote more. What does n of t represent? Remember, we are the ones making the convention. So we are the ones deciding what n represents. What did we decide to do? Who can tell me what I wrote? Very good, Emily. So n of t represents population of wolves t years after 2011. Okay, population of wolves t years after 2011. So if they are telling us that in 2011 there were 129 wolves, what does that mean? What's t? What is t in this case? What's the value of t in this case? Are you sure about that, Sebastian? Very good, Maria. T is equal to 0, right? Basically, what they're saying is that when t is 0, n is 129 because 2011, that's 0 years after 2011, right? So basically, the information in the first sentence is that if you plug in 0 into the function n, you're going to get 129. You understand this? This is important because nobody's going to tell you this. You have to be able to write this down by reading the problem. Remember, we are translating this into mathematics now. Okay? Decided what n of t was. We decided that it meant population of wolves t years after 2011. So with that in mind, then we need to write down the data that's given to us. They say that in 2011 there are 129 wolves. That's the initial amount, right? And how do we write the initial amount? That's what happens when t is equal to 0 at the beginning. When t is 0 at the beginning, there were 129 wolves. Do you understand this? Is everybody else okay with this? Yes, Maria.
So I don't know if you saw that I wrote n plus 129.
Yes,
So I
I saw that, but
yeah, so I put that because I had understood that since that's the initial value, like when time is 0, so we have to start like adding on top of the 129.
no. Remember, we're being told that the population grows exponentially, right? So we have a shape for the function. That's what we wrote in the first part. Something times a to the t. Now what we need is we need some data points to figure this out. Like I said, this problem is just like number 1. It's just that we first need to get the information out of the problem so that we are in the situation like number 1, that you had 2 points and we found A and B, right? So far we only have found 1 point. right?
Okay.
So here, remember, here you don't add. Sebastian, no, it's not like that. Like think about it. If you say that n of t is equal to 129 to the t power, that doesn't make sense, right? First of all, when t is equal to 0, then n is 1, according to your formula. And as this is expressing, when t is 0, n better be 129. That's the beginning, right? So you have to be careful. Okay, again, all we're doing is trying to come up with, 2 points like these ones. See, like in number 1 that I gave you 2 points and asked you for exponential function. Well, we're trying to come up with these 2 points. Right now we have one, the point 0,129. That's 1 point on the graph of this function, for sure. Okay, we just need another one because 1 point is not enough. There are infinitely many exponential functions passing through any given point. Now, if you have 2 points, that's a different story. Then there would be 1. Okay, so let's go to the next sentence and repeat. By 2013, the population had reached 236 wolves. What does that mean? So what is this third sentence telling us? So what do we gain from this third sentence? Anybody? Okay, which one do you think it is, Maria? We just did the second sentence, so we are looking at the third sentence, right? So what is that sentence telling us? No problem. If you understood the first, what we just did, you should be able to answer this other question. What is this sentence telling us? Very good, Ramses. This means that 2 years, right? Because 2013 means 2 years after 2011, right? So we are just being taught here that when t is 2, n is 236. So that means that when you plug in 2 into n, we get 236. All right, so we're good now because we have everything we need. We know that we're looking for an exponential function, and we know already 2 points on the graph of this function. Now we are in the situation just like in problem number 1. So now it's just a matter of finding a and b. We're about to do that now. But before we do that, any questions? Any questions on how we found this information? How we're going to find the function? Okay, we're just translating the problem. All right, so n of 0 equals 129. That's another thing that we have. So we have that n of 0 is 129. And then we also have that the value of the function at 2, what was that? 236. 236. Okay, so now with this information, let's go ahead and let's figure out the formula for the population of wolves. All right, so again, n of 0, this is telling me that if I plug in 0, what do we get? So we're going to get b times a to the 0. And by the way, for any exponential function, every time that you plug in 0, what do you get? Get this guy here, right? Because a to the 0 is always equal to 1. So this number b, it has a name. It's called the initial value of the population. Okay, that's well, in this case, the initial value of the function. But for application problems, it's always the initial value. Anyways, n of 0 is equal to 129, and therefore b is 129. Okay, because a to the 0 is equal to 1. All right, so here we use the fact that, this is equal to b times 1, which is b. All right, so b is 129, so that means that so far our function is looking like this. 129 times a to the t. Okay, so now we have to figure out what a is from the remaining information. So we're being told that if we plug in 2, then we're going to get 236. So let's do that. So n of 2 equals 236. This is going to give us then that n of 2 is 129 times a squared, and then 236 equals 129 times a squared. So what is a? We get 236 over 129. Sure, that is a nice little number. It is not. So let's just write it like this. Let's see, 12, I can do 3, 9, 11. Okay, 3 is not good there. So then a is going to be, remember here you have two choices, plus or minus square root of this number. And as you know, a has to be positive, right? Because a is positive, then it's going to be the positive version of this. 236 over 129, the square root, okay? Right, so this is the exact value of a, so that's the one that we're going to work with. So that means that our function n of t is going to be equal to 129 times square root of 236 over 129 to the fifth power, okay? And of course, if you want to make a little bit more sense of this, then let's see, 236 divided by 129 square root, we get about 1.35. So we can approximate this to 129 times 1.35 to the t. That's just an approximation. The exact value is this one right here. Okay. Questions? Did you understand? So notice that there were several steps involved being able to solve this problem. First, we needed to model the situation, meaning we're given a problem, then we're saying, okay, what does our function n represents? So this right here, this first part is critical. If you don't tell me what n means to you, then you won't be able to make sense of the following sentences in the paragraph. Okay? So we decided that n means population evolved 3 years after 2011. So based on that, then we were able to come up with the other data. It looks exponential, that's given to us. So we have the general form, and then we get the two data points from each of the sentences. And it's critical to understand that 2011 means t is 0, 2013 means t is 2. Okay? Once you have that, then it's the same thing that we did for number 1. Plug in, get your equations, and then start solving. In this case, it was easy because when you plug in 0, the a is gone, so you immediately got b for free. And then, find a, you just use the data point, and we're done. And so, for example, why something like this is maybe meaningful, let's say that, a little question, what will be the population in 2020? So according to this model, and assuming that the wolves just keep on growing and there is nothing in the wolf or nothing, they just keep on growing, following this model, what will be the population in 2020? So if we want to answer this question, what is it that we need to do? Let's see, and round to the nearest integer. Okay. So can anybody tell me what will be the answer? What will be the population in 2020? So to answer this question, what do we need to do? N of what? What is t? Very good. So that would be n of 9, right? So roughly, if we plug in 9, what do we get? N of 9. So we raise that base to the 9th power, and then times 129. So we get around 1,954, or maybe you may want to say 955. Let's see, I would say about 1,954, and then there is another wolf that is about to be born, because it's 54.5. But for sure there will be around 1,954, and then seems to be one that is about to be born halfway through pregnancy. Okay, anyways, questions? Questions on this? All right. And there is another more interesting questions that you could ask that actually it's the one that we want to be interested about. But before we do that one, we're gonna do problem 3. You know, the other interesting question is, well, maybe there is a certain number of words that you may start getting worried about. Let's say, I don't know, 5,000. So it would be nice to see, you know, when is it that how long until the population reaches 5,000? Because the moment that it reaches that number, it may start to become a problem. I don't know, nearby areas or whatever that may be. So you may want to know how many years do we need to wait until the population reaches 5,000? That's a more interesting question. But to answer that question, you know, we need to wait a little bit because this is a question about finding t. And you know, do that with the knowledge we have so far is not enough. That's actually when logarithms come into play. We're going to come back to this. Before that, let's go ahead and let's do number 3. In homework, you have stuff like number 3 as well. So I want to make sure that you understand how to deal with those problems. Okay, so I'm going to come back to the wolf question. But before we do that, let's take a look at problem 3 that we have above. So let's see, this one is about depreciation. And then here we're being told that, let's see, a vehicle purchased for 29,800 depreciates at a constant rate of 8%. Determine the approximate value of the vehicle 13 years after purchase. So do you guys understand the question? You know, as you know, if you buy a car today, you know, as time passes, the price of the car is going to go down, right? The value of the car goes down, it depreciates. So if you want to sell the car 13 years from now, of course, it's going to be for way less than what you pay today because of depreciation. And then, of course, this is not taking into account other factors, like, for example, cars from the 1950s. A good car from the 1950s now actually probably more expensive than what it cost back then. I would say most likely it is, but that's another thing, right? Because it's an antique and it's actually a luxury to have that car. But just plainly looking at depreciation, the more time passes, you know, the value of the car gets reduced. We're not taking into account here, you know, other things like, you know, antiques and so on. Anyways, in this case, you go ahead, you buy yourself, I don't know, a Honda Accord, 39,800, and then you know that it depreciates 8% every year. And the question is, what will be the value 13 years after the purchase? So, everybody okay with this? Right, so we'll see. We'll figure out whether that's correct or not. It's okay, Sebastian. So, any questions with what the problem is asking? Do you understand what the problem is saying? All right, so then let us try to figure out a formula for the price of the car, right? The value of the car. And then, you know, we just have to figure out what will be the value after 13 years once we come up with the formula. So let's go ahead and let's do something similar to what we just did. Let's see, for number 3, let us define our function. Let's see, let's use Sebastian's point of view. Let's use v for value. So let v of t represents the value of the, so they don't say car. What did it say? Vehicle. The value of the vehicle, let's say t years after purchase. Okay. So value of the vehicle, t years after purchase. Okay, that's what VLT will represent. The value of the vehicle t years after purchase. And again, we don't know whether this is going to be an exponential model or not because we're not being told. So this is something that we have to figure out on our own. So what we're being told is that the vehicle depreciates at a constant rate of 8% every year. Okay, so we are also being told that the original value, the initial value, sub price of the vehicle, what was that? It was 39,800, right? So that means that when t is equal to 0, that means the initial value of the car is 29,800. Make sure that the number is correct. Right, so that's what we get from the first sentence, right? 29,800. That's the value of the car when t is equal to 0. And then we would like to know what's the value of the car 13 years after purchase. In other words, the question is, so what do we want? So we want to know what's the value of V of 13. This is really what we are after, okay? So V of 13 is gonna tell us what the value of the car is 13 years after purchase. Okay, so let's see. Let us try to calculate some values to hopefully get some idea of what's going on here. So we know that V of 0 is equal to 29,800. That's right after purchase. Now, what will be the value of the car 1 year later? In other words, instead of writing, so remember, V of 0, okay, I'm going to do like a little table. I'm going to write here T, and then we're going to write here the value of the car. Okay, so let's see. When T is 0, then the value of the car is 29,800. Okay, so when T is 1, how do we calculate the value of the car? Anybody? So in other words, 1 year after purchase, how do we calculate the value of the car? It's going to be 29,800, the original value, minus, that's the depreciation, 8%, right? Because it gets depreciated at a rate of 8% every year. So minus 0.08 times 29,800. Does everybody understand this? All right. So, you could calculate what this is, but remember, we are after a formula. So I'm going to start playing with this a little bit. Notice that I can factor out the 29,800, okay? And then we're going to have 1 minus 0.08, okay? Which, let me leave it like that because that's going to tell us something interesting. And then, of course, then you can write this in a very more simpler way. Let's leave it like that. Okay, so let's see, year 2, so 2 years after purchase, what's the value of the car? Again, it gets depreciated by 8% the previous amount. This is every year, okay, the previous amount. So what's the previous amount? The previous amount is V of 1. It's going to be 29,800 times that parenthesis. So I'm going to write that previous amount. This is the value of the year before, and then it gets depreciated 8%. So 0.08 times V of 1. Okay? So notice that we can factor out here V of 1 again, just like we did what we did above. So you see the pattern. This guy right here was V of 0. Okay? Remember, this was V of 0. So we can factor out V of 1, and then we're going to get 1 minus 0.08. All right? But then remember, notice that V of 1 is 29,800 times 1 minus 0.08. So this is just going to be 29,800 times 1 minus 0.08 squared. And hopefully you start seeing a pattern here. I'm going to do it one more time. Notice that this is to the first power, and then t is equal to 1, that's the power that you have here. If t is equal to 2, that's the power that you have here. And everything else is the same. So what would be the guess? When t is equal to 3, what are we expecting to get down here? Expecting to get 29,800 times 1 minus 0.08 cubed, right? So that's what we are expecting. Let's see if indeed that's the case. Let's calculate it. So after 3 years, what's the value of the car? Its previous value. So the value after 2 years minus the depreciation that happens from year 2 to year 3, which is 8% of that value. And once again, we can factor out V2, so we get our 1 minus 0.08. And then when you put it what V2 is, then indeed we get the required expression. So as you can see, this is gonna keep on happening, right? So this keeps on happening. So moral of the story, what will be V of t? So after t years, what will be the value of the car? Is gonna be equal to 29,800 times 1 minus 0.08 to the t power, right? Because the value of the year is what goes there. Of course, we can write this more nicely as 0.92. So it will be 29,800 times 0.92 to the t. So moral of the story, when you're dealing with this type of depreciation, as they say at a constant rate, is depreciated at a constant rate of 0.08%, this is actually, how you can find the formula. So notice that the number that we have in front of the parentheses is the initial amount of the object that's being depreciated, and then the rate is actually what you're going to be using to figure out the base of your exponential, okay? And it's always 1 minus depreciation rate. That's what we just figured out here. Okay, so let me write down the full formula. So V of t, I'm going to work with the simplified version. And now that we have the formula, then we can write the answer. So what's the answer? V of 13. So this is going to be 29,800 times 0.92 to the 13. So let's find the price of this car or vehicle, whatever that is. And don't round. You only round at the end, okay? Don't round in between steps. Right, so and we're getting here 10,079.94. I'm rounding to the nearest cent here, okay? So after 13 years, the price of the car, the price of the vehicle will be $10,079 with 94 cents. Okay, questions? Questions on this example. This is different than the others, okay? The others, you were given points and we're finding the formula. Here, we use the context of the problem to figure out the formula. And is this depreciation phenomenon, okay, at a constant rate? So this gives you an exponential behavior, as we saw. Okay, any questions? Right? Is everybody else okay? You have several questions like this in the homework. Okay, so this is how you can deal with them. So it's about depreciation. There are also questions about things that gain value. They appreciate at a certain rate. For example, think about a bank account and that kind of stuff, right? With interest rates and so on. And then for that, you need to use the appreciation. So instead of subtracting, you will be adding, right? So you have the initial amount, and then you're gonna be doing 1 plus the rate at which that amount is being appreciated. Okay? Appreciation that you get. Again, it really depends on the problem. But my advice is just read the problem at hand and then have this sort of mindset when you're looking at the questions. Right. Are we okay with this? Okay, so to make the transition now to the next question, we could either use this vehicle example and ask ourselves, okay, maybe you want to sell the car when, I don't know, when the value reaches $5,000. So another question to ask is, how long do you need to wait until the value of this car depreciates to 5,000? Okay, or something like that. Or we can use the wolf population and ask a similar question. How long do we have to wait until it reaches 5,000 wolves? I'm just using 5,000. That's the number of the day. But it doesn't have to be 5,000. Okay? Let's see. Since we're here, we're talking about this depreciation business. Let's use this as our example. So a natural question to ask here is, how long until the value of the car or of the vehicle, until the value of the vehicle reaches or depreciates to 5,000. Okay, so how long do we need to wait? How many years must pass until it reaches 5,000? We know there will be more than 13 years, right? Okay, so and of course this is assuming the same conditions of the problem. So in other words, what is it that we are asking? So we want V of t, the value of the vehicle, to be equal to 5,000, and then the question is really about finding t. Does everybody understand this? All right, so we want to figure out t. So in this case, let's see, what do we have? So we have 29,800 times 0.92 to the t. This is our function, and we want this to be equal to 5,000, and we want to find for t. We want to find t. Well, we can start doing what we normally do, right? So you would divide. So we have 5,000 divided by 29,800, and even simplify a little bit. But then we reach a point at which we feel, what's going on? What do we do here? A little bit stuck. So we reach this expression. 0.92 to a t equals 50 over 298. Okay, good. What's t? So the question is, to what power do we need to raise 0.92 to obtain 50 over 298? You can even, figure that out. 50 divided by 298. That's about 0.1677, etc. To what power do we need to raise t to obtain this number? This doesn't seem like a trivial question. If it was, again, 2 to the t equals 8, well, it would be easy, right? The power is 3, and then you're good to go. But how do we do this? So this is the next kind of problems that we are concerning ourselves with. How do we solve this type of non-trivial, I guess, exponential equation? This is a little exponential equation. It's just that it is a little bit less trivial than the ones that we dealt at the beginning today. So, do you understand the question? All right, so let's see how we might try to answer this. How can we answer something like this? Well, let's see, what do we have? Notice that here on the left-hand side, so if you think about what's going on here, on the left-hand side, we have an exponential function, right? Base 0.92, the input to this function is t. And then we're being told that the output is 50 over 298. So we know the output is a number. So what do we have? We have our function. We go back to our box. Remember our machine point of view. So we have our function v of t here. And okay, so I guess that's looking at the origin, at the equation here. So to probably okay. So when I write v of t, then that means I'm referring to the line above. Okay, but it's really irrelevant. Really, the point is that we want to know t. Okay. But I guess to be technical, I want to be referring to this line here, so I should probably not call it v of t. So let me see. So we have here the machine 0.92 to a t. Okay, because I don't want to introduce a new letter, so that's why I'm writing the formula. So, and what do we know about this little machine? T is coming in, and what we know is that the output of this is gonna be 50 over 298, right? Of course, our job is to figure out what is t. This is what we want to know. So you have this machine and you know the output of it. So you have this function, you know the output of it. We want to figure out what input produced that output, right? This is really what we are after. Everybody okay with this? Okay, so does this bring something into mind? In other words, we want this output. We would like to come up with another machine so that this output, we put it into this machine, and then magically we want this machine to give us back the t that we needed. that we originally inputted. Is this bringing something into mind? This reminds you of something. Very good, Maria. So what we are actually looking for in here is the inverse, right? So we would like to have here the inverse of the first function that we were given. If we manage to make sense of that, then we're going to be able to solve this problem, right? So in other words, we need to answer the question, what do we need? We need the inverse of the function y equals 0.92 to the t in this particular case, right? So if we manage to figure out what the inverse of this function is, then that's it. We put it in that little blue box. 50 over 292 will come in, and then the output of this inverse is going to be the t that we are after. Does everybody understand this? Okay, very so. And how do we do this? So then, several questions come to mind. First question is, does this inverse exist? Because as you know, not every function has an inverse. So does this inverse exist? That's the first question that we need to answer ourselves. Let's see, can you tell me, is there such an inverse? Will this inverse function exist? What do we need to look at for this function to ensure the inverse? Very good, Maria, it exists. And why does it exist? What do we know about exponential functions? It's one-to-one, very good. So since the function 0.92 to a t, remember the way that this function looks like is, base is less than 1, so it has this general behavior, okay? Since this function is one-to-one, an injective function, then the inverse exists. So we know that there is an inverse. All we have to do is find it, okay? Then the inverse exists. And what is this inverse? Well, this is actually what we call logarithm, okay? This is what we call logarithm. In other words, a logarithm is just the inverse of a corresponding exponential function. That's all it is. Okay? So whenever you say the word logarithm, you're talking about the inverse of some exponential function. Now, of course, you need to tell me what exponential function you are finding the inverse. Okay? So the inverse of what exponential function, and all you have to do is tell me the base. Okay? That's why logarithm, they come with a base. In this case, it will be logarithm with base. In this particular problem, the base is 0.92, right? So when you tell me logarithm with base 0.92, you are telling me this is the function that is the inverse of 0.92 to the t. This is the inverse of that particular exponential function that we're talking about. In other words, the word logarithm always comes attached with another data, the base, because you need to tell me the inverse of what exponential function you are, okay? There are many logarithms out there because they all correspond to every different exponential function that you can write down. Do you understand this? Do you understand that logarithm is just the inverse of an exponential? I mean, this is the definition. There is really nothing to understand. But do you see the relationship? When you see the word logarithm, that's just a fancy word, okay, or inverse of a certain exponential function, okay? So that's what we're gonna start studying next, logarithm. But this is what it's coming from. So let us make sense of this. I'm gonna write down what logarithm is and so on, and then we're gonna start practicing how to evaluate, how to calculate logarithms, and then we're gonna come back and we're gonna be able to answer this question. Okay? So let's do that. So again, I guess right here, let me make another analogy. Notice that we have this function, this exponential, and what is it that we're looking for? We're looking for t, okay? And t will turn out to be the output of this inverse function, which is the logarithm. So when you look at an exponential function, that exponent is just the logarithm that you need. So for example, if you know that t to the 3 equals 8, immediately by looking at this, what can we say about the logarithm? I'm going to use words now. So what can we say about the logarithm base 2 Remember, you always need to tell me the base. This means this is the inverse function of 2 to the x. So this right here is just telling me, okay, this is the inverse of 2 to the x, okay? What will be logarithm base 2 of the number 8? So remember, all we are saying with this little sentence, logarithm base 2 of 8, we're just referring to this little exponent up here, okay? So that equals 3. Because all we are saying is 2 to what power is equal to 8? That's what we are asking whenever you want to calculate a logarithm, okay? Remember, you are undoing the exponential behavior. So if you know that 2 to the 3 power is equal to 8, that means logarithm base 2 of 8 must be 3, okay? So this guy right here is the logarithm base 2 of 8, okay? Do you understand this? All right, so again, let's make this a little bit more formal, and then we're gonna come back and we're gonna take a look at this, okay? So I guess, okay, sorry, I keep going back and forth. So let me finish here. So with this language that I'm introducing here, then we could say that then the t that we're looking for is gonna be logarithm. So logarithm base 0.92 of 50 over 290, right? So once we learn how to calculate logarithm with base 0.92 of something, then we can come back and finish answering the question, right? All we need to do now is make sense of what is this. How do we calculate something like this? So that's what we're about to discuss now. Everybody okay? All right, so let's do it. So that's section 4.3, and it has to do, it's about logarithmic functions. Okay, so again, the way we're going to define it is just as the inverse of the exponential function. So recall, and if you have the function f of x equals a to the x, a positive and different than 1, then something like this is an exponential function. So I'm just saying that we're going to talk about logarithmic functions now. Can you hear me? Okay, very good. So again, let's remember, so we have an exponential function with, what's the setup? We have an exponential function a to the x with base positive and different than 1, with an exponential function. So this is also is an exponential function, and it is 1 to 1. And it is 1 to 1, as we saw earlier, and therefore it has an inverse. 1 to 1, and so it has an inverse. Okay, so then that's our definition. What's the definition of logarithm? It's just the inverse of the corresponding exponential. So definition, the inverse of the function f of x equals a to the x with a positive and different than 1 is called, the inverse of this function is called, now we have a name for it, it's called logarithm. So it's called logarithm with base a. Again, it should be clear why, because the base of the exponential is a. Logarithm with base a, and the way we write it and is written as follows. So instead of writing the words that I've been doing in the previous page, logarithm base something of something, what we write is, okay, this is the inverse of the function, and we have a special way of writing. We write the letters log, log, so that stands for logarithm. Then here we put the little number that represents the base of the log, and then inside this parenthesis we put the argument of the logarithm. Okay, And remember, this a is exactly the same as the base of the original exponential function. So it comes with its own restrictions, okay? So what are the restrictions? A must be positive and different than 1, okay? Those are the same restrictions that we have in the exponential function. In other words, a here, this is the base, okay? And then what you put here inside this parenthesis, this x right here, that's the argument. In other words, the input, okay, of a function as the input. And then the output is the whole thing, the logarithm base a of x. The way you read this is logarithm base a of x. But once again, all this means is that this is the inverse of the corresponding exponential function, okay? So I don't want you to get confused. Remember, this x is not this x. Remember, what happens when you go to the inverse? X and y are switched, right? So if you want, this x right here that we have in the argument, it represents the y of the exponential function, because they are inverse to each other, right? So x and y's are exchanged. So the x that you have here in the argument represents the y of the original exponential function. So let me write this in a more systematic way. So if you are told that y equals log base a of x, this is equivalent to say what? So remember, the y in this inverse function was the original input of the exponential, and the x in this inverse function was the output of the exponential. So this is the same thing as saying a to the y is equal x. Okay? As if you write it this way. If you write it the other way, if you write that, or I guess you could also say, if you write that y equals a to the x, it's the same thing as saying then that x must be log base a of y. Any of the two boxes are okay. I'm going to be working with the one in red, but they are the same. Remember, the point is that x and y's input and output are swapped between the two functions, because they are inverse of each other. So whatever is the input in the log, that becomes the output in the exponential. And whatever was the output in the log, that's the input of the exponential, and the other way around. Okay? So as a point, here x is the input, it became the output in the exponential side. Here y is the output, it became the input in the exponential side. And then notice that the base, of course, is the same for both of them. Okay? So, the easier way to look at it is, if you want to write the corresponding exponential statement to a logarithmic, all you do is, base to this power, this number, equals this guy. Okay? So, a to the y equal x. That's a very easy way to remember that. In this case, that would be a to the x equals y. Okay? All right. Anyways, questions about this definition? Questions? Yes, Maria?
So in the last equation you wrote, y equals log, that's times x or to the x?
No. Okay, I didn't put this, but usually we don't write the parentheses.
But that's
We write the parentheses when
times x, right?
No. All that is, so look at this part right here. Okay, so that's the definition. This is how we write the log. This is just a notation. If you write the word log, this has no meaning. You need to tell me log of what.
Okay.
It's like if I write this, what do we mean by this? I need to tell you what is it that we're doing the square of, right? Like it's not clear. Yeah, square, but square of what? That's not enough. So I have to say, okay, x. Okay, x squared, right? If I do that, then now you know what I mean. It's the same thing here. If I write log base a, then the question is, yeah, okay, but what? Log of what? And that's what goes in here. All of that is one package. Okay? So let's see. You do log parentheses, and then the stuff that you write in here, that's what you are calculating the log of. So there is nothing being multiplied here. There is no product here. This is just one thing. Okay? So unless you tell me what goes in here, then this has no meaning. Right? That's the argument of the function. It's the same thing as this has no meaning, right? You need to tell me what is it that you are squaring for this to have a meaning. Okay. Everybody okay? So usually, usually we don't write the parentheses, but if you want to make it more clear, you can write parentheses. For example, if you usually write log base 2 of 8, okay? But what this really means, whenever you write it like that, this really means log base 2 parentheses 8. It's just that you're not going to be seeing the parentheses unless you have a big expression inside the argument. Like, I don't know, log base 2 of x plus 3. If you write something like that, then that's a different story. Then you have to write parentheses because this is different than just saying log base 2 of x plus 3. You put parentheses, this is one thing, and then you're adding 3 to it. If you want x plus 3 to be in the argument, you need to write it like this. Okay? You okay? Any questions so far? All right, so then let's go ahead and let's calculate this. So let's see, how do we calculate this? All right, so for example, let's figure out what is log base 2 of 8. So evaluate. And for example, let's say that we want to do log base 2 of 8. So remember, how can you do this? Well, one way to think about this is you can turn this into an equation, okay? For example, you can say, imagine that this is equal to some number, let's call it y. And to solve this equation, to solve this problem, what do you do? Well, this is the same thing as saying, using our little box, 2 to the y equals 8. And then you can see here that this means that y must be 3. So log base 2 of 8 equals 3. And the motivation is because 2 to the 3 is equal to 8. So really the question that you need to ask yourself when you see this is, whenever you see this, you need to ask yourself, okay, this is going to be equal to a number. What number is this? It's whatever power you can raise to that will give you 8. So you ask yourself, 2 to the what power equals 8. And whatever answer you come up with, that's the output of this. In this case, this is 3 because 2 to the 3 power equals to 8. You guys understand this? You understand how to... Right. So remember, log is a power, right? What power? The power that you have to raise 2 to obtain 8 in this case. Let's see. Let's do another one. How about log base 3 of 1 over 27? So how do we compute this? Very good. Very good. So to what power do we need to raise 3 to obtain 1 over 27? So if you don't see that, once again, just call this y, and figure it out. So this means, right as an exponential, 3 to the y is equal to 1 over 27. So to what power do I need to raise 3 to get 1 over 27? And now you solve it. So 27 you can write as 3 cubed. So this is 3 to the negative 3, right? Because, okay, let me do this. So we can write this as 3 to a negative 3, and therefore it follows that y equals negative 3. Okay? So log base 3 of 1 over 27 equals negative 3. Questions? Questions on this? Okay, let's see. How about this? What would be log base 5 of 5? Anybody? Very good. This is equal to 1. Once again, you need to ask yourself, 5 to what power equals 5, right? Well, that's 5 to the 1, right? So this is certainly equal to 5. And the justification, since 5 to the 1 equals 5. Right, good. How about this? Log base 5 of 1. What is this? Anybody? So what's the question that you need to ask yourself? Ask yourself the question. 5 to what power equals 1? Very good, Sarah. This is 0. Remember, anything to the 0 power is equal to 1, right? Since 5 to the 0 equals 1. Okay, questions? Questions, please? Right. So this is the first skill that you need to learn, okay? So you have to be able to use this box back and forth. What do I mean by this? When I say back and forth, I mean the following. If you're given a logarithmic expression, sometimes it's convenient to write it exponentially. In other words, you know the expression on the left, and then we want to write the expression on the right. So given a logarithmic expression, how do you write it? It's equivalent exponential form. And also the other way, if you are given an exponential form, how do you write it as a logarithm? Okay, so let's practice this next. So that would be the next set of examples that we're gonna do. So example, write the logarithmic expression in its equivalent form. Let's go from log to exponentials. So write the logarithmic expression and of course logarithmic expression means an expression that contains logarithm, right? In its equivalent exponential form. Right, so let's see, let's do log base a of 4 equals 5. Oh, okay. Right, so let's do this one. Then I'm gonna, I wanted to do something else before this. But anyways, let's just do this one. So log base a of 4 equals 5, and then b, I'm gonna write log base e of b equals -3. Okay, so let's write this down. So the first one, how do we write this in exponential form? This is just using the box. So remember, what does this mean? The term on the left means what power do you need to raise a to get 4? And we're saying is that the power is 5. That's what this means. We're saying that if you do a to the 5th power, you get 4. That's what that statement is telling us. So this means a to the 5th equals 4. Everybody okay with this? Like I said, it's very simple. State the base, raise it to this power, and then equal to the argument. Okay, a to the 5th equals 4. Let's see, following this logic, how b? How can we write b in exponential form? Second problem here. Very good. B to a -3 equals b. Good. So, everybody okay with this? Given a logarithmic expression, you understand how to write it equivalently as an exponential form? In exponential form? All right. So now we're gonna do it backwards, but before I do that, let me introduce some notation that I forgot to write earlier. So definition. There are two special type of logarithms that we have a special notation for. Okay? The first one is what we call the common logarithm. Okay? The notation that we use for it is like this. There is a logarithm that we write, and we don't put any number here. So notice that here where the base should be, we don't write it. Whenever you see this, and there is no base, it's understood that what we mean by this is log base 10 of x. Okay, so this is called the common logarithm. It's called common logarithm. And because you don't see any little number down there where the base should be, it is understood that yes, there is a base, but it's base 10. Just like when you write a square root of something, we don't write the index here, we don't put a 2. It's understood that if you don't write anything, it means square root. If you want to mean something else, then you need to specify, right? Well, that's the same thing. For logs, if you don't write anything where the base should be, then it's understood that the base is 10. That's called common logarithm. And then another one that's used a lot is what we call the natural logarithm. So the notation is ln of x, okay? And then this is just logarithm with base e, okay? So this is called the natural logarithm. Keep my color coding the same. So this is called natural logarithm. Again, these are just conventions. These are just definitions. Basically, whenever you see ln, that means log base e of x, and whenever you see log of x and no base whatsoever, it's understood that the base is 10. For example, if you look at your calculator, most calculators, scientific calculators, to calculate ln, most of them, they're not going to allow you to use whatever base you want, but you're going to see two keys, one that says ln, another one that says log. Okay, so the ln key, that one is for natural logarithm. The log key, that one is for the common logarithm, base 10. We're going to be using those to be able to, calculate some logarithms that are not straightforward. Anyways, for example, b above, log base e of b, we can write it as ln of b. That's the same thing as what we had in part b above. So if you write that ln of b equals -3, then you need to understand that when you see this, that makes log base e. So the exponential form is e to the -3 equals b. Are we good with this? Do you understand this notation? ln is base e. It's right there on the screen. Whenever we write ln of x, remember, so first of all, this doesn't mean anything. You write ln, that doesn't mean anything. Okay, you need to tell me what goes here. So ln of something. So if you write ln of x, then that just means log base e. Okay, so ln just means that the base is a logarithm. The base of the logarithm is the number e. Okay, that's all I have said. You guys okay? All right, so let's see. Let's do let's now practice going back. I give you exponentials and you write it as ln. So example. So write the exponential expression. Write the exponential as a logarithm. Okay, so first one we have, let's do 1.2 to the m equals 3. Then here let's do 8 to the 4 equals 24. Let's do here 10 to the x equals 47. And let's do here e to the t equals 9. Okay, so let's write each of these guys as logarithms. All right, so the first one, we have 1.2 to the m is equal to 3. What will be the corresponding log? Remember, logarithm is a fancy word for exponent. Okay, so whatever exponent you have here, that's the one that's equal to the logarithm. So this is going to be m equals to, then you write your log, and then the same base that you have on the exponential, of course, is going to be the same base that you have on the log, and then, it's clear that the 3 has to go in the argument. Okay? And then you can always visually quickly check by converting back in your mind, like 1.2 to the m equals 3, that's exactly what we have. Okay? So what will be this one? Again, 4 is the log, right? And that means that it's going to have log base a of 24 is equal to 4. Okay? For c, again, the same thing. So here x is the log because that's the exponent. And this time, because the base is 10, no need to write it. That's a common logarithm. So it's understood that we mean log base 10. And for the last one, what is this? E is the exponent, so that will be the log. And because the base is e, instead we have a special notation for it. We write ln. So t equals ln of 9. Okay, questions? Okay, and for example, notice that in here, let's say, what would be x in this case? Notice that in this problem, x is the power that you need to raise 10 to get 47. If you want to figure this out, get your calculator and then find a log of 47. So if you do log of 47, we get about 1.67. See, I'm going to write 21. I'm doing an approximation there. So that means that if you do 10 to this power, you're going to get 47 or something, close to it. Of course, to be exact, you need to write the exact, but it seems to be an irrational number. Okay? And if you want to calculate what's ln of 9, you just have to use your calculator, put 9 and do ln of 9. So this is about 2.1972. Okay? So if you do e to this power, you're going to get 9. Of course, the exact version of it. If you do that approximation, you're not going to get exactly 9. You're going to get something close to it. All right. Any questions? So the same way that if you want to know what's square root of 13, you put in a calculator. Well, the same thing. If you want to know what's ln of 9, you have to put in your calculator. Okay. All right. Questions? Okay. So let's see. Let's try to answer the card question. So remember that we left a question hanging here, right? So what we're doing, we had this car, and we wanted to figure out what was the value of the car. So how long we needed to wait until the value of the car reaches 5,000, right? That was the question that we wanted to answer. So let's go ahead and let's try to answer that question. So let's see. I remember what was happening there. Let's see. Okay, so back to the vehicle question. That was an example, another example. So let's finish the vehicle question. So remember, we knew that the formula for the vehicle was, so we figured out that it was 29,800 times, what was it, 0.92? Times 0.92 to the t power. And then the question that we're trying to ask is, how long until the value of the vehicle depreciates to 5,000. Okay, so how long do we need to wait until the price of the vehicle is 5,000, is valid? All right, so as we discussed earlier, to do this, we really are asking for, the solution to this equation. B of t equals 5,000, and then we want to know what's the value of t. So we already worked this out, right? So this equals 5,000, and then we came up with the point that 0.92 to the t was equal to, what was it, 50 over 298, right? And we were stuck here because we didn't know how to figure out t. Well, now we can do a little bit more, right? Now we can at least write an expression for t. Let's see. This is an exponential expression. So if you want to isolate t, if you want to solve for t, what should we do? We need to write this as a logarithm, because after all, t is a logarithm. It's the exponent. So let's see, can anybody tell me what would be t equal to in this case? So let's write this as a logarithm. It would be t equals to, so what's the equivalent expression? That would be log base 0.92 of 50 over 298. Very good. So everybody okay with this so far? Does everybody understand this? If we manage to calculate this, then we know what t is. Now, of course, if you have a calculator, at this point we use calculator. If you have a calculator that allows you to input any base you want, then you can just go ahead and put this and you get the value. Now, most calculators will not allow you to do this. Like the one that I have right now, for example, only allows me to do ln or log. Okay? So not good, but not every calculator does. So what do we do in this case? Well, there are properties of logarithms that we can use. We're going to be talking about this next time. I'm going to use one of those just to finish this problem, which is the change of basis property. Basically, the change of basis allows you to change the base of your logarithm to whatever base you want. In this case, of course, for calculation purposes, we either change it to base e or base 10. And then, of course, what you get in return in exchange for this, for doing this change of basis, is that you need to do a division. Okay? Basically, this property that I'm about to use is what we call change of basis. We're going to talk about this next time. Change of base. That will be discussed next time. And basically, what it allows me to do is to say that this is the same thing as saying, okay, I'm going to use ln. You can use log. It doesn't matter. You can put your favorite base. In fact, those of you that have that can use a calculator to put the base, calculator with 0.92, and then check that you should get the same answer as I do. So it's going to be ln of 50 over 288 divided by ln of 0.92. Notice how we change the basis of the first logarithm, which was 0.92, we change it to base e. So what you do is you have to divide. So basically the property says if you have log base a of something, this is going to be equal to log base c of x over log base c of a, where c is any base that you want. If you pick c equals e, that will be ln of x over ln of a. You could pick c equals 10, that would be log of x over log of a, and so on. Anyways, we'll do that next time. So let me go ahead and let's calculate this. So what do we get? So we get 50 divided by 298, and then I'm gonna do ln of that. Okay, so I'm getting like about negative 1.780507, and then in the bottom, let me store this in memory. Then in the bottom I have 0.92 ln of that, so it's like negative 0.0833816, and then when we do the quotient, so this guy divided by the other guy, hold on. So that will be this divided by this one. Okay, so we get that t is about 21.4. So let's round it to the first decimal place. Or if you want, yes, 21.41. Let's see, I'm going to leave it in 21.4. So remember, this represents years. So what does this mean? That in about 21 years and a half, the price of the car is going to be around $5,000. Okay? Okay, Anyways, questions. Again, we're going to talk about the properties and this change of base that I just did later on. But any questions on the idea of logarithm and how to actually, go back and forth? You see how useful it is to know how to go back and forth from logarithm to exponential, because that's actually what you're going to use to solve some equations. Okay. Here we had this little equation, and we're able to solve it by writing that exponential statement as a logarithm. Then we immediately got out t out of, we got what t was equal to in that case. All right.